There is a particular kind of silence that falls over the natural world when something enormous goes wrong. Not the silence of peace, not the silence of a calm night in an open field, but the silence of absence. The silence that follows when something that was always there suddenly is not. Imagine stepping outside on a clear night. The stars are visible. The darkness is deep, but something is different. Something above you. Something that has hung in the sky for as long as your species has existed, as long as any animal on this planet has ever drawn breath, is simply gone. The moon is not there. At first, perhaps, the mind refuses to register it. It searches for clouds, for an angle, for an explanation. But the sky is clear, and the stars are sharp, and the space where the moon should be is occupied by nothing at all. That moment, that imagined moment of realization, is where this documentary begins. Not because it is a comfortable thought, but because understanding what the moon does for this planet requires, first, understanding what a world without it would become. And that journey, from the familiar sky above your head to the profound, ancient, often invisible role our moon plays in nearly every system that makes this planet habitable, turns out to be one of the more remarkable journeys available to human curiosity. Because the moon is not merely a light in the night sky. It is not decorative. It is not incidental. It is in ways that scientists are still actively working to quantify. One of the central reasons that complex life on Earth exists at all. That is a remarkable statement, and by the end of this documentary, you will understand exactly why it is almost certainly true. The moon is the most familiar object in the night sky, across all of human history, across every civilization, every culture, every generation that has ever lived on this planet. The moon has been there. It has regulated calendars. It has inspired mythology. It has guided the tides and the migrations of animals and the menstrual cycles of early humans who first noticed the connection. It has been the subject of more poetry than perhaps any other natural object in existence. And yet, precisely because it is so familiar, it is easy to stop seeing it clearly. Most people understand, in a general way, that the moon causes tides. Ask almost anyone and they will tell you that. But ask them how, or why, or what those tides actually do for the planet beyond moving water up and down a beach, and the answers grow quickly uncertain. Ask whether the moon affects the speed at which Earth rotates, and the question feels strange. Surely a distant rock cannot influence the rotation of an entire planet. Ask whether the moon stabilizes Earth's axial tilt, and many people have never considered the question at all. This is the peculiar nature of the moon. It is the most visible object in the night sky, and simultaneously one of the least understood in terms of what it actually provides to the world below it. The moon is 384,400 kilometers away on average. That distance changes slightly as the moon travels along its elliptical orbit, drawing closer at perigee and retreating further at apogee. It is large enough, relative to the Earth, that scientists sometimes refer to the Earth-Moon system as a double planet, rather than a planet with a satellite. The moon's diameter is about 3,474 kilometers, more than a quarter of Earth's own diameter. For comparison, most moons in the solar system are tiny fragments compared to the planets they orbit. Ours is conspicuously, unusually large. That unusual size is not a coincidence, and it is not irrelevant. To understand what we would lose without the moon, we first need to understand how we got it. Because the origin of the moon is itself one of the most dramatic events in the history of this solar system. And it is an event that set the stage for nearly everything that followed. About 4.5 billion years ago, the solar system was a very different place. The sun had recently ignited. The planets were still forming, pulling themselves together from clouds of gas and dust and rocky debris. Earth itself was younger than it is possible to truly imagine. A molten, churning world, its surface constantly remade by the impact of countless smaller bodies falling inward from the outer regions of the forming solar system. The early solar system was chaotic in a way that makes the word chaotic feel insufficient. Objects of enormous size moved on unstable orbits. Planetary bodies that had gathered mass over millions of years could find themselves on collision courses with other bodies that had done the same, and approximately 4.5 billion years ago, one of those collision courses ended, a body roughly the size of Mars. Astronomers have given it a name, Theia, was traveling along an orbit that brought it into the path of the young Earth. The details of what followed are still being refined. But the broad outline is clear from the evidence preserved in the rocks of both Earth and Moon. The collision was not a direct impact, in the way we might imagine a meteor striking the ground. It was more of an oblique blow. Theia striking Earth at an angle, the two bodies briefly merging and then catastrophically separating, with the outer material from both bodies being flung into orbit around the newly combined mass. What happened next took perhaps decades, perhaps centuries, fast by cosmic standards. The debris that had been thrown into orbit began to coalesce. Gravity drew it together, piece by piece, ring by ring, until the fragments had accumulated into a single large body. The Moon. This is called the giant impact hypothesis, and it is supported by a remarkable convergence of evidence. The Moon's composition closely matches Earth's mantle. The ratio of isotopes in Moon rocks and Earth rocks is nearly identical, a chemical fingerprint that strongly suggests they share a common origin. The Moon is depleted in volatile elements, consistent with material that was subjected to enormous heat before cooling in space, and the angular momentum of the Earth-Moon system is consistent with a massive oblique impact. The collision also did something else, something whose consequences would echo for billions of years. It tilted Earth. The impact altered Earth's axial tilt, the angle at which our planet leans relative to its orbit around the Sun. And that tilt, currently sitting at roughly 23.5 degrees, is one of the reasons Earth has seasons. It is one of the reasons that temperate zones exist. It is one of the reasons that large portions of the planet are neither perpetually frozen nor perpetually baked. But here is the detail that matters most for our story. That tilt is not perfectly stable on its own. Over very long timescales, the gravitational influence of other planets, particularly Jupiter and Saturn, would tend to perturb it, to cause it to wander, to make it shift dramatically over millions of years. The way the tilt of Mars has shifted, turning that planet's poles from warm to frozen and back again through enormous cycles of climate catastrophe. Earth's tilt does not wander that way. And the primary reason is the Moon. The Moon acts as a gravitational anchor. Its mass and the gravitational coupling between the Earth and Moon system stabilizes the axial tilt within a relatively narrow range. Not perfectly. Over very long timescales, the tilt does oscillate, contributing to the cycles of ice ages that geologists have traced through billions of years of rock. But the range of that oscillation is modest compared to what it would be without the moon's stabilizing presence. Remove the moon, and Earth's axial tilt becomes vulnerable to perturbations that could, over millions of years, send it drifting wildly. Some computer models suggest it could eventually reach angles approaching 90 degrees. Others suggest more moderate, but still dramatic swings. The precise outcome is difficult to calculate across such timescales, and scientists continue to debate the details. But the broad picture is consistent across multiple lines of research. Without the moon, Earth's climate history would likely have been far more chaotic. And chaotic climate history means a very different story for life. Before we get to what a moonless Earth might look like over millions of years, there is a more immediate question. What would happen in the days, weeks, and years immediately following the moon's disappearance? And to answer that, we need to understand something that most people know about but few have thought through deeply: the tides. The tides are caused by the moon's gravity pulling on Earth's oceans. But that simple sentence hides a mechanism worth understanding. Because the tides are not simply the moon pulling water toward it. They are the result of a gradient, a difference in gravitational pull across the diameter of the Earth. The side of Earth facing the moon is pulled slightly more strongly than the center of Earth. And the center of Earth is pulled slightly more strongly than the far side. This differential, this gradient, stretches the Earth very slightly in the direction of the moon, creating two tidal bulges simultaneously, one on the side facing the moon and one on the opposite side. The oceans, being fluid and responsive, rise into those bulges. The land, being solid, responds too, though far less dramatically. The solid Earth actually flexes by several centimeters with each tidal cycle. The sun also contributes to the tides, with roughly 46% of the tidal force that the moon provides. When the sun and moon align at new moon and full moon, their tidal forces combine into what are called spring tides, the highest and lowest tides of the lunar cycle. When they are at right angles, at quarter moon phases, their forces partially cancel, producing neap tides. Now, here is what most people do not know. The tides do not merely move water. They transfer energy. They create friction. And over billions of years, that friction has had a profound effect on Earth itself. As Earth rotates beneath the tidal bulges, friction between the tidal bulges and the solid Earth acts as a brake, very slowly, by about 2 milliseconds per century. The rotation of the Earth is being slowed down. The tides are lengthening the day. 4 billion years ago, Earth rotated much faster. A day on the young Earth lasted somewhere between 6 and 10 hours. Over billions of years, the tidal braking effect of the moon, and to a smaller degree the sun, has slowed that rotation to the 24-hour cycle we know today. Where does the rotational energy go? It transfers to the moon. As Earth loses rotational energy, the moon gains orbital energy and slowly spirals outward. The moon is currently moving away from Earth at approximately 3.8 centimeters per year, about the same rate at which fingernails grow. A century from now, the moon will be roughly 4 meters further away than it is today. A billion years from now, it will be measurably more distant, and solar eclipses, as we know them, with the moon's disk precisely matching the sun's, will no longer be possible. This relationship between Earth's rotation, the moon's position, and the transfer of energy is one of the most elegant gravitational dances in the solar system. It is also one of the most consequential ones. Without the moon, The tidal braking that has been gradually slowing Earth's rotation would largely disappear. The sun's tidal influence would continue, but at less than half the strength. And the consequences of that would ripple through every system on Earth. If the moon were to disappear tonight, the immediate change in Earth's rotation would be essentially zero. The slowing effect of tidal friction operates over geological timescales, not human ones, but over millions of years, and over the billions of years before the moon's hypothetical disappearance. The absence of the moon's tidal braking would have left Earth rotating significantly faster. What does a faster rotating Earth look like? It is a planet under different physical stress. A faster rotation means stronger Coriolis forces, the deflection of moving air and water caused by the planet's spin. Stronger Coriolis forces mean more energetic atmospheric circulation. And more energetic atmospheric circulation means stronger, more frequent, and differently structured weather patterns. The wind systems that currently distribute heat, moisture, and energy across the globe. The trade winds, the jet streams, the Hadley cells that govern tropical circulation would be organized differently on a faster rotating planet. Storms would be more intense. Weather patterns would shift. The distribution of rainfall and drought across the continents would change in ways that are difficult to predict precisely, but impossible to ignore in principle. There is another effect of faster rotation that is less immediately obvious, but perhaps even more consequential. The shape of the planet itself. Earth is not a perfect sphere. It bulges slightly at the equator because the centrifugal effect of rotation throws material outward. A faster rotating Earth would bulge more. The equatorial regions would be slightly further from the center of the planet, and gravity at the equator would be slightly weaker. The polar regions would be somewhat more compressed. This equatorial bulge affects ocean circulation, atmospheric dynamics, and the very distribution of land masses over geological time. Some researchers have also proposed that faster rotation might affect the behavior of Earth's magnetic field. The vast invisible shield generated by the movement of molten iron in Earth's outer core. The relationship between rotation rate and magnetic field strength is complex and not fully understood, but it is a relationship, and changes in one potentially influence the other. The magnetic field is critical for protecting Earth's atmosphere from the solar wind. The stream of charged particles constantly emanating from the sun, a weakened magnetic field over long timescales, could allow the solar wind to gradually strip away the atmosphere, as appears to have happened on Mars billions of years ago. These are slow processes. They operate over millions and billions of years. But the early solar system lasted billions of years before complex life emerged on Earth. And the conditions that allowed that life to emerge were shaped by the steady, cumulative influence of those same slow processes. Here is something worth pausing on, because it is one of the more surprising chapters in the story of life on Earth. The tides did not merely shape physics. The tides may have shaped biology. For the first several billion years of Earth's history, life was microbial. Bacteria and archaea colonized the oceans, developed photosynthesis, and eventually, in one of the most consequential events in biological history, began releasing oxygen into the atmosphere in quantities large enough to permanently change the chemistry of the air. But for most of that time, the living world was aquatic. The transition from ocean to land is one of the pivotal events in the history of complex life, and the tidal zones The intertidal zones, those strips of coastline that are covered by water at high tide and exposed to air at low tide, may have played a crucial role in making that transition possible. Organisms living in the intertidal zone face a cyclical challenge that no deep ocean organism faces. They must be able to survive both in water and in air. They must be able to tolerate desiccation during low tide and submersion during high tide. They must be physiologically flexible in ways that pure aquatic creatures do not need to be. Some evolutionary biologists have proposed that the tide zone functioned as a kind of training ground for terrestrial adaptation. Species that evolved mechanisms to survive regular exposure to air in the intertidal zone were, in a sense, pre-adapted for a more permanent transition to land. The cyclical pressure of the tides drove the evolution of physiological flexibility that would later prove essential for the colonization of terrestrial environments. This is not a settled theory. Evolution is complex, and the full history of the ocean-to-land transition involves many factors, but the broad logic is compelling. Without large tides, the intertidal zone would be far narrower and less dynamically challenging. The evolutionary pressure that drove organisms toward air-breathing adaptation would have been weaker. The timeline for the emergence of land animals, if it happened at all, might have been very different. There is another connection between the moon, the tides, and the origin of life that is even more speculative but worth understanding. Some researchers have proposed that before life began on Earth, the tidal cycling of shallow coastal pools could have concentrated and cyclically wetted and dried the chemical precursors to biological molecules. Amino acids, nucleotides, lipids, creating the conditions for chemical reactions that might have led to the first self-replicating molecules. This is sometimes called the tidal pool hypothesis for the origin of life. Again, not settled science. The origin of life is one of the most actively debated areas in all of biology and chemistry, and multiple different environments have been proposed as the crucible where life first emerged. Deep sea, hydrothermal vents, volcanic hot springs, even interstellar space. But the tidal pool hypothesis raises a haunting question. Is it possible that the moon was not merely a witness to the emergence of life on Earth, but a participant? We mentioned earlier that the moon stabilizes Earth's axial tilt, but it is worth returning to that point in more detail, because it is possibly the most dramatic way in which the moon shapes the conditions for life on this planet. Earth's axial tilt, currently 23.5 degrees, is what gives us seasons. As Earth orbits the Sun, the northern hemisphere tilts toward the Sun during northern summer and away from it during northern winter. This variation in solar angle drives the temperature differences between seasons, the migration of animals, the growth cycles of plants, the patterns of rainfall. The seasons are fundamental to the ecology of this planet, at every scale from the microscopic to the continental. But the tilt does not stay at exactly 23.5 degrees. Over a cycle of approximately 41,000 years, the tilt oscillates between about 22.1 and 24.5 degrees. This is a relatively narrow range, about 2.4 degrees of variation, and it is one of the drivers of Earth's ice age cycles, which have alternated with warmer interglacial periods on a similar timescale. The moon's gravitational influence is responsible for keeping this oscillation within that narrow range. Without the moon, computer simulations suggest that the axial tilt could wander far more dramatically. Some models show it potentially reaching 85 degrees or more over tens of millions of years. Others show more moderate, but still substantial swings of 20 to 30 degrees. To appreciate what these numbers mean, consider what happens at extreme tilts. At a tilt of 85 degrees, Earth would be essentially lying on its side relative to its orbit. The poles would face the sun directly for months, receiving intense solar radiation and heating to temperatures far above what they experience today. Then, 6 months later, they would face away from the sun entirely, plunging into months of total darkness and cold. The equatorial regions, meanwhile, would receive the sun at a very shallow angle for most of the year, making them relatively cool. The entire pattern of climate zones, the tropics, the subtropics, the temperate zones, the polar regions, would be fundamentally reorganized. Mars provides a real-world example of what can happen to a planet without sufficient axial stabilization. Mars has small moons, Phobos and Deimos, but they are tiny and have little stabilizing effect. Mars's axial tilt has varied widely over its history, shifting between roughly 10 and 60 degrees over millions of years. Some researchers believe these tilt variations played a significant role in the catastrophic climate changes that transformed Mars from a world that may once have had liquid water on its surface into the frozen desert it is today. Earth's moon is simply larger, much larger, relative to our planet, than the moons of Mars are relative to theirs, and that size difference is responsible for an enormous difference in axial stability, an enormous difference in climate predictability, an enormous difference in the conditions available to evolving life. Life can adapt to a great deal. Evolution is extraordinarily flexible over long timescales. But there are limits. Rapid, large-scale climate shifts, the kind that could result from dramatic axial wandering, put enormous pressure on ecosystems. They drive extinctions. They eliminate niches faster than organisms can evolve into them. They disrupt the long, slow ecological stability that seems to be necessary for the emergence of complex, multicellular life. Whether life would have emerged at all on a moonless Earth, or whether it would have remained microbial, or whether it might have taken dramatically different forms, is a question that cannot be answered definitively. But the question itself reveals something important. The moon is not a peripheral feature of this planet's story. It may be one of the central chapters. It's return to the present day and to the thought experiment that opened this documentary. The moon disappears tonight. What happens immediately? In the first hours, the most obvious change is darkness. The moon, even at its full phase, provides a significant amount of light, enough to cast shadows, enough to read by, enough to navigate a familiar landscape. The full moon illuminates Earth's surface with a brightness roughly 400,000 times less than the midday sun, but enough to profoundly affect the behavior of nocturnal animals. With the moon gone, nights during what would have been the full moon phase would be substantially darker. Not completely dark. Starlight and airglow remain, but noticeably, measurably darker. This change in nighttime light levels would have immediate biological consequences. Species calibrate their behavior to the lunar cycle. Sea turtles use the reflected moonlight off the ocean surface to orient their hatchlings toward the water. Coral reefs synchronize their spawning to the full moon, releasing eggs and sperm in mass spawning events timed to the lunar calendar. Numerous species of insects, birds, and mammals have behavioral patterns, foraging, migration, reproduction, that are synchronized to moonlight levels. Some of these adjustments would be relatively rapid. Evolution is slow, but behavioral flexibility is fast. And many of these lunar synchronized behaviors are at least partially plastic, adjustable within an individual lifetime, but others are deeply embedded in physiology. The circulunar rhythms, biological clocks tuned to the roughly 29.5-day lunar cycle, are present in the cells of many organisms. Disrupting them would cause physiological stress, even if not immediate extinction. The tides, meanwhile, would continue, not disappear. The sun's tidal influence would still operate, producing tides with approximately 46% of the amplitude that we currently experience. The twice-daily rhythm of high and low tide would persist, but weakened. Coastal ecosystems adapted to the current tidal range would face significant pressure. The intertidal zones that currently host some of the most biologically diverse ecosystems on Earth would shrink dramatically. But wait, there is something else that would happen. Something that very few people think about when they imagine the moon disappearing. The Earth-Moon system has a center of gravity. It is not at the center of the Earth. It is displaced toward the moon, sitting inside the Earth's body, but offset from the planet's geometric center by about 4,700 kilometers. This point is called the barycenter. The Earth and Moon do not orbit each other the way a ball orbits a string, with the string's endpoint stationary. Instead, both Earth and Moon orbit around the barycenter. The Moon's orbit takes it far from the barycenter, tracing a wide circle in space. Earth's orbit around the barycenter is a much smaller wobble, but it is real and measurable, and it has consequences. This wobble affects Earth's orbit around the Sun in subtle ways. It contributes to the slight eccentricity, the slight elliptical shape of Earth's path. It interacts with the gravitational influences of the other planets. It is part of the complex gravitational ecology of the solar system. If the Moon were to disappear, Earth's orbital wobble around the barycenter would also disappear. Earth's path around the Sun would become slightly different. The interactions between Earth and the other planets would change, in subtle but potentially accumulating ways over very long timescales. This is not an immediate catastrophe. These are changes that operate over millions to hundreds of millions of years. But they are real, and they illustrate something important. The Moon does not merely affect Earth's surface and atmosphere. It is part of the gravitational architecture of the inner solar system. Oceans are not passive containers of water. They are active, dynamic systems that transport heat, regulate climate, cycle nutrients, and sustain the bulk of Earth's biological productivity. And the Moon plays a significant role in keeping those systems functioning. The tides drive what oceanographers call tidal mixing, the turbulent churning of ocean water that prevents the ocean from stratifying into completely distinct layers. Without tidal mixing, the deep ocean and the surface ocean would become more isolated from each other. The deep ocean is cold and rich in nutrients that have sunk from above. The surface ocean is warmer, and where sunlight penetrates, where photosynthesis can occur, where the base of the marine food chain operates. Tidal mixing allows nutrients from the deep to reach the surface and allows surface water to be mixed downward. This vertical exchange is important for the productivity of marine ecosystems, particularly in regions where the ocean is otherwise stratified. in a world with reduced tidal mixing, which is what a moonless world would have, the efficiency of this exchange would decrease. The productivity of the surface ocean would be affected. The food chains built upon that productivity would feel the pressure. There is a further connection between the moon, the tides, and ocean circulation that operates at an even larger scale. The tides interact with the submarine topography, the underwater mountains, ridges, and trenches to generate internal waves that carry energy through the ocean interior. These internal waves contribute to the mixing processes that help drive the global ocean circulations, sometimes called the ocean conveyor belt or thermohaline circulation. Thermohaline circulation carries warm water from the tropics toward the poles, and cold, dense water from the poles toward the tropics along the deep ocean floor. This global circulation is one of the primary mechanisms by which heat is redistributed across the planet. It moderates the climate of regions like Western Europe, which would be far colder than it is without the warm North Atlantic current delivering heat from the tropics. It drives the deep oxygenation of the ocean, bringing oxygen from the surface into the deep ocean and making the deep ocean habitable for the organisms that live there. The moon's tidal influence contributes energy to this system. How much? This is an area of active scientific research, and the numbers are still being refined. But the contribution is not negligible. A moonless ocean would be a differently circulating ocean. A differently circulating ocean would distribute heat differently, and differently distributed heat would mean different climates for different regions of the planet. There is a dimension of this story that we have not yet properly explored, and it is the dimension that most immediately connects the moon to human experience. The moon is the basis of time, not just as a metaphor, not just as an inspiration for poetry about passing months. The moon's 29.5-day cycle from new to full and back to new was, for essentially all of human history until relatively recently, the primary unit of medium-term time measurement. Month, the word itself, derives from moon. In many languages and calendrical systems, the connection is even more explicit. The Islamic calendar is purely lunar. The Hebrew calendar is lunisolar, reconciling the lunar month with the solar year. The Chinese traditional calendar is lunisolar. The Hindu calendar systems are lunisolar. Across vastly different cultures, independently, human beings looked at the sky and found in the moon's cycle the most natural and reliable unit of time between a day and a year. But the moon does not merely provide a calendar. It synchronizes the biology of the planet, spawning events in coral reefs, migrations of certain fish species, the egg-laying cycles of horseshoe crabs, the emergence of the Pacific palolo worm, which rises to the ocean surface in such enormous numbers during specific lunar phases that Pacific Islander communities have harvested it as a food source for centuries, knowing with confidence the precise lunar conditions under which it will appear, the flowering times of certain plants, the breeding cycles of certain mammals, including, some researchers argue, ancestral humans. The moon has been a biological clock for the living world for hundreds of millions of years. In a moonless world, these synchronized events would decouple. Some would simply shift. Organisms are adaptable, and many of these lunar synchronizations likely evolved in response to the moon's light and gravity, meaning they could, in principle, evolve away from the moon. But evolution takes time, deep time, and the disruption in the interim could be severe for ecosystems built upon the reliable timing of spawning events and migrations. Horseshoe crabs, for example, emerge in enormous masses on North American beaches during specific spring tides to spawn. Shorebirds time their northward migration to arrive at those beaches precisely when horseshoe crab eggs are most abundant. A caloric resource so rich that it effectively enables the birds to fuel their migration to the Arctic. The entire cascade of biological events is synchronized by the lunar cycle. Disrupt the moon, and you disrupt the horseshoe crabs, and you potentially disrupt the shorebirds, and you affect the Arctic ecosystems those birds reach, and the insects they eat, and the plants those insects pollinate. These cascading connections are the reason ecologists speak of keystone species and keystone processes. The moon may be one of the more significant keystone influences on the ecology of this planet, not by acting directly on individual organisms, but by providing the rhythmic structure around which enormous numbers of biological processes have organized themselves over evolutionary time. Here is where the journey becomes genuinely difficult to navigate. Because we are moving from the relatively well-understood physics and ecology of a moonless world into a domain where the uncertainties multiply rapidly. Would life still have emerged on a moonless Earth? Almost certainly, yes. Life on Earth is extraordinarily resilient, and the conditions for the origin of life, liquid water, energy sources, the chemical raw materials needed for the first biochemistry, do not require the moon. The deep-sea hydrothermal vents that are one proposed site for the origin of life would have been unaffected by the absence of the moon. The chemistry of prebiotic Earth would have been different in some ways, but not necessarily inhospitable to the emergence of self-replicating molecules. Would multicellular life have emerged? This is harder. The moon's stabilizing effect on Earth's axial tilt and its contribution to the tidal dynamics that may have driven the evolution of intertidal life means that the conditions favoring the evolution of complex multicellular organisms would have been different, not necessarily absent, but different. The Cambrian explosion, that remarkable period approximately 540 million years ago when the fossil record suddenly fills with evidence of diverse complex animals, remains one of the most intensely studied and debated events in evolutionary biology. What triggered it? The explanations are many and contested. Rising oxygen levels, changing ocean chemistry, the evolution of predation, ecological cascades. The moon is not typically listed among the primary causes, but the moon shaped the ocean chemistry, the tidal dynamics, and the axial stability that provided the backdrop against which the Cambrian explosion occurred. Would it have happened on the same timeline without the moon? Would it have happened at all? These questions cannot be answered with confidence. Evolution is a contingent process, sensitive to initial conditions and historical accidents, in ways that make counterfactual histories deeply uncertain. What can be said with some confidence is this: the moonless Earth would have been a different Earth. The climate would have been more variable over geological time. The tidal zones would have been narrower. The axial stability that may have allowed ecological niches to persist long enough for evolution to develop the complexity that leads toward multicellular life would have been reduced. Whether intelligence would have evolved on such a world is even more uncertain. Human intelligence is the product of billions of years of evolutionary history under specific conditions. change those conditions significantly, and the evolutionary path diverges. Whether that diverging path leads anywhere near intelligence as we know it, or whether it leads somewhere entirely different or nowhere that resembles complex animal life at all, is a question that current science cannot answer. But asking the question reveals something important. The moon is not an accessory to the story of life on Earth. It may be one of the story's architects. There is one more connection that is worth exploring before we move into the second half of this documentary, because it touches on something that most people never associate with the moon at all: Earth's magnetic field. Earth is surrounded by an invisible magnetic field, generated by the movement of molten iron and nickel in the outer core. This field extends tens of thousands of kilometers into space, deflecting the stream of charged particles, the solar wind, that flows constantly outward from the sun. Without this magnetic shield, the solar wind would interact directly with the upper atmosphere, gradually stripping away lighter gases. Over hundreds of millions of years, this process could erode the atmosphere significantly. Mars, which lacks a strong global magnetic field, has almost certainly lost much of its early atmosphere to exactly this process. Mars may once have had an atmosphere thick enough to support liquid water on its surface. The evidence for ancient river valleys, lake beds, and ocean basins is substantial. But over billions of years, without a magnetic shield, the solar wind gradually eroded that atmosphere. Today, Mars's atmosphere is about 1% as thick as Earth's, and any surface liquid water is impossible. The moon does not generate Earth's magnetic field. That field is generated entirely by processes within Earth's own interior. But the moon may influence how long Earth's core retains the heat that drives those processes. The Earth's magnetic field is generated by the movement of molten iron in the outer core, a movement driven by the gradual cooling and solidification of the inner core, and by convection currents within the outer core itself. The rate at which the core cools is influenced by the rate at which heat flows from the core to the mantle and from the mantle to the surface. Some researchers have proposed that the moon's tidal influence, which flexes not just the oceans but the solid Earth itself, contributes energy to the interior of the planet, slowing the rate at which the core cools. If this is correct, the moon may be modestly extending the lifetime of Earth's magnetic field, and thus modestly extending the timescale over which Earth retains its atmosphere. This connection is more speculative than some of the others we have discussed. The contribution of tidal heating to the Earth's thermal budget is thought to be relatively small compared to the radiogenic heat from the decay of radioactive elements in the crust and mantle. But the possibility cannot be dismissed entirely, and it raises a striking image: the moon, hanging in the sky above, indirectly contributing to the invisible shield that protects everything below. We have been moving between time scales, from the immediate effects of lunar disappearance to the geological timescales of axial drift and climate change, to the evolutionary timescales of billions of years. Let us now focus on a middle timescale, centuries and millennia. If the moon were to disappear, what would human civilization experience over the next few hundred to few thousand years? In the first decades, the changes would be primarily astronomical and ecological. The night sky would be darker. Tidal patterns would shift toward the weaker solar tides. Coastal ecosystems would begin adjusting to the new tidal regime. Species with strong lunar behavioral synchronization would face stress, Some would adapt. Others, particularly those with the most rigid lunar dependencies and the smallest populations, might decline. Navigation would change. For most of human history, the moon was one of the primary tools of navigation, both at sea and on land. In the modern era, satellite navigation has supplanted lunar navigation for most practical purposes. The disappearance of the moon would not meaningfully affect the GPS system or the satellites that support it. Agriculture, which historically depended heavily on the lunar calendar for planting and harvesting schedules, has also largely transitioned to solar and meteorological timekeeping in modern industrial farming. The loss of the moon would not directly disrupt modern agricultural supply chains, though it would be culturally disorienting in regions where lunar calendars remain in daily use. The psychological impact is harder to quantify, but impossible to ignore. The moon is woven into human culture at a depth that goes beyond religion, beyond mythology, beyond poetry. It is part of the cognitive landscape of what it means to live on this planet, to look up at the sky and see something familiar looking back. Its absence would be a kind of grief. Not merely the grief of loss, but the grief of a world fundamentally changed in a way that cannot be undone. Over centuries, the tidal rhythm of the oceans would continue on a solar schedule. Coastlines would adjust to new patterns of erosion and deposition. Fisheries that depend on tidal cycling would produce differently. Some of the biological abundance associated with high tidal range, the richness of the intertidal zone, the concentration of nutrients driven by tidal mixing would decrease. Over millennia, the effects on Earth's rotation would begin to be measurable, though not yet significant. The day would slow slightly less quickly than it does now, since the moon's braking effect would be absent. In practical terms, across a few thousand years, this would mean days that are lengthening at a slower rate. Not a change that human beings would notice within a lifetime, but detectable across centuries. The axial tilt, as we discussed, would be vulnerable to slow drift. Over thousands of years, the drift would be small. Over tens of thousands of years, it might begin to shift the climate zones in detectable ways. Over millions of years, the consequences could become severe. We have now traveled through the immediate aftermath, the ecological consequences, the evolutionary implications, the geological timescales, and the deep history of the moon's role in shaping this planet. And we have arrived at the edge of what science currently knows. With confidence, there are things about the moon's influence that are well established. The tides and their dynamics, the slowing of Earth's rotation, the stabilization of the axial tilt within its current range, the lunar synchronization of many biological processes. These are measured, quantified, and supported by substantial evidence. There are things that are strongly supported, but still being actively researched. The precise contribution of lunar tidal stabilization to preventing catastrophic axial wandering, the role of tidal mixing in ocean circulation and climate, the evolutionary significance of the intertidal zone, the possibility that lunar tidal pools contributed to the origin of life. And there are things that remain genuinely uncertain. Whether complex life would have emerged on a moonless Earth, whether intelligence would have evolved under different conditions of axial variability and climate chaos, what the full extent of the moon's influence on Earth's magnetic field might be over geological time. These uncertainties are not failures of science. They are frontiers. They are the places where the questions have not yet yielded to the accumulated weight of evidence and analysis, and they are worth naming honestly, because the unknown is not a reason to diminish the story. It is part of the story, because what this journey has revealed, even before we enter its second half, is something that the familiar view of the moon from a backyard on a clear night does not immediately suggest. The moon is old. It formed in fire, from catastrophe, from the impact of a world-sized body against the young Earth. It has been receding slowly ever since, moving away at a few centimeters per year, carrying with it the energy stolen from Earth's rotation. For 4.5 billion years, it has been there, stabilizing the tilt, driving the tides, slowing the days, anchoring the axial angle that gives us seasons, contributing to the tidal dynamics that may have driven life out of the ocean and onto the land. And in all of that time, it has never asked to be noticed. It has simply done what gravity and physics required of it. But notice it we should, because the second half of this story is where the consequences become truly planetary in scale, where the question of what would happen without the moon reaches its full scope, and where we encounter perhaps the most unsettling realization of all. The moon is not permanent, not in the cosmic sense. It is slowly leaving, and the changes it is setting in motion, the slowing of the day, the recession of the orbit, the gradual weakening of the tidal influence, are happening right now, at this moment, as the moon rises over whatever horizon is currently yours. There is a detail in the story of the moon that most people have never heard, and it changes the nature of this entire documentary in a subtle but important way. We began this journey by asking what would happen if Earth lost its moon forever. We imagined the moon vanishing, a sudden catastrophic absence, and exploring that thought experiment has revealed the extraordinary scope of the moon's influence on this planet. But here is what makes that thought experiment more than merely hypothetical. The moon is already leaving, slowly, imperceptibly slowly by any standard that a human lifetime can register, at approximately 3.8 centimeters per year, less than the width of a finger. The moon is receding from Earth, not because anything is pushing it away, but because the same tidal forces that have been slowing Earth's rotation have been transferring angular momentum to the moon, gradually nudging it into a wider and wider orbit. At the current rate, 1 million years from now, the moon will be roughly 38 kilometers further from Earth than it is today. 1 billion years from now, it will be nearly 38,000 kilometers further away. These distances sound enormous, but the moon is already nearly 400,000 kilometers away. So the percentage change across even 1 billion years is not dramatic. The moon is not going to spiral away into deep space on any near-term astronomical timescale. But its influence is gradually diminishing. The tidal forces are gradually weakening. The braking effect on Earth's rotation is slowly becoming less effective. The day is getting longer. The tidal mixing in the oceans is very slowly becoming less vigorous. The stabilizing effect on Earth's axial tilt is very slowly decreasing. This is happening at a rate so slow that no human being or any civilization likely to exist on Earth in the next several thousand years will notice any difference. But over hundreds of millions of years, the changes accumulate, and Earth's geologic past actually contains evidence of a time when the moon was much closer, and the world was consequently very different. Travel back in time, not by a few thousand years, but by several billion. The early Earth, in the immediate aftermath of the giant impact that formed the Moon, would have been barely recognizable. The Moon, newly formed from the debris of that catastrophe, was much closer to Earth than it is today. How much closer? Estimates vary, but in the very early period following the Moon's formation, it may have been as close as roughly 20,000 to 30,000 kilometers from Earth's surface, compared to the current average distance of about 384,000 kilometers. At that proximity, the tidal forces would have been extraordinary. Not merely stronger than today's tides, vastly stronger. The tidal bulge raised in the Earth's oceans by a moon 10 or 20 times closer would have been enormous. The solid Earth itself would have flexed dramatically with each tidal cycle. The frictional heating generated by that flexing could have been significant, contributing to the geological activity of the young planet, the early Earth, still cooling from the heat of accretion and the giant impact, with its crust only beginning to solidify, with its ocean only recently condensed from the steam that had been the atmosphere of the molten world. This early Earth experienced tides that dwarf anything in Earth's geological memory. Tides that would have swept coastal areas with waves tens or hundreds of meters high, if any coasts yet existed to receive them. And the day, the length of Earth's rotation, was much shorter, perhaps 6 hours, perhaps 8. The Coriolis forces driven by that rapid rotation would have made the atmosphere a dramatically different engine than it is today. The storm systems, the circulation patterns, the distribution of energy from the tropics to the poles, all of it organized around a planet spinning nearly 4 times faster than Earth does today. Over the subsequent billions of years, the Moon receded, the day lengthened, the tides moderated, and Earth gradually became the world we know. The transition was not smooth or sudden. It took billions of years of slow, continuous change, but the direction was consistent. Earth with a closer Moon was a more energetic, more tidally stressed, more rapidly rotating world. Earth with a more distant Moon is a calmer, more stable world. In a very real sense, the Earth we inhabit today, with its 24-hour day, its moderate tidal range, its stable axial tilt, is the product of 4.5 billion years of the Moon gradually moving away. We are living in a particular moment in that long recession, a moment that happens by accident to be well suited to complex life, and a moment from which things will gradually continue to change. On time scales so vast they challenge the imagination. We have been speaking, theoretically, about what a moonless Earth might look like. But there is a world in our own solar system that provides something close to a real-world comparison, and examining it adds texture and urgency to the story. Mars. Mars is smaller than Earth. It has 2 moons, Phobos and Deimos. But they are tiny, lumpy, irregular rocks captured from the asteroid belt, with diameters of 22 and 12 kilometers respectively. Their combined mass is negligible compared to our Moon. For all practical purposes of axial stabilization and significant tidal influence, Mars has no meaningful Moon. The consequences are written clearly in the geological and climatic history of Mars. Mars's axial tilt has varied dramatically over its history, swinging between roughly 10 and 60 degrees over periods of millions to tens of millions of years. During low tilt periods, the poles become colder, and carbon dioxide from the atmosphere freezes out onto the polar caps, thinning the atmosphere and reducing the greenhouse effect. During high tilt periods, The poles warm and the polar ice sublimates, thickening the atmosphere. The entire Martian climate flips between dramatically different states on timescales that are, in geological terms, relatively rapid. This is not merely a theoretical argument. Mars's poles show evidence of extensive layered deposits, the residue of successive cycles of ice accumulation and ablation as the axial tilt varied over time, the evidence for ancient liquid water on Mars. The river channels, the lake beds, the mineralogical signatures of water-rock interaction suggests periods when the Martian climate was dramatically more hospitable than it is today, and the evidence for what happened to that water, where it went, why Mars dried out, points toward the catastrophic climate instability that axial wandering produces. There is another dimension to the Mars comparison. Mars lost its global magnetic field early in its history, probably within the first few 100 million years. Without a magnetic shield, the solar wind had direct access to the Martian atmosphere. Over billions of years, the solar wind stripped away much of that atmosphere. Today, Mars's atmospheric pressure is less than 1% of Earth's, making liquid water thermodynamically impossible on the surface, and making Mars inhospitable to life as we know it. Did the absence of a stabilizing moon contribute to Mars's fate? It almost certainly contributed to the climate chaos that led to the freezing of Mars's surface water. Whether it contributed to the loss of the magnetic field is more speculative. But the axial instability that plagued Mars, combined with its smaller size, and therefore faster core cooling rate, produced a world very different from Earth. A world that had what appeared to have been the raw ingredients for life: water, energy, organic chemistry, but lost the climatic stability needed to allow life to take hold and persist. Earth, with its large moon and its stabilized axial tilt, avoided that fate, at least so far. And understanding that Mars narrowly missed having conditions for a very different history, and understanding that the difference may partly come down to having or not having a large moon, puts our own moon in a new light. We have touched on the fact that the early Earth rotated much faster than it does today. But there is a detail in that faster rotation that connects to the origin of life in a way that is both surprising and compelling. Some researchers studying the conditions necessary for the emergence of life have proposed that the length of the day, the period of the rotation cycle, may matter for the energetics of primitive photosynthesis and the cycling of chemical precursors of life. On a faster rotating Earth, the day-night cycle would repeat more frequently. Solar energy would be available in shorter, more frequent bursts, rather than in the longer, more sustained periods that characterize a 24-hour day. The thermal cycling of surface environments, the daily warming and cooling that drives the concentration of chemical compounds in shallow water environments, would operate on a shorter period. Whether a shorter day favors or disfavors the emergence of life is genuinely uncertain, and this area of research is still early. But the connection is worth noting because it illustrates a principle that runs through this entire story. The Moon's influence on Earth's rotation has had consequences that reach into every corner of the planetary system, including potentially into the very conditions that allowed life to emerge in the first place. There is also a connection between the length of the day and the structure of the atmosphere. A faster rotating planet has stronger Coriolis forces, as we discussed, which affects atmospheric circulation patterns. But it also affects the distribution of solar energy. On the young, rapidly rotating Earth, each part of the surface was exposed to sunlight more frequently and for shorter periods. The diurnal temperature range, the difference between daytime and nighttime temperatures, would have been different. The nighttime cooling period, which affects the formation of dew and the cycling of moisture, would have been shorter. These details may sound technical and perhaps peripheral, but they are the kinds of details that, accumulating over millions of years, shape the chemical environment in which prebiotic chemistry occurs. They are part of the reason that the specific Earth we inhabit, the one with its current day length, its current axial tilt, its current tidal dynamics, may have been particularly favorable for the emergence and persistence of life. And the Moon is the reason the day has the length it does. Without the Moon's tidal breaking, Earth would still be spinning at something much closer to its original rapid rate. The day would be far shorter. The world would be a fundamentally different place. Let us now spend some time in one of the most profound consequences of a moonless Earth: the fate of the seasons. Currently, Earth's axial tilt of 23.5 degrees gives us a beautifully calibrated seasonal system. The tropics receive relatively consistent solar radiation year-round, making them permanently warm. The polar regions receive radiation at a very shallow angle, with long summer days and long winter nights, creating extreme seasonal variation. The temperate zones experience moderate seasonal swings that drive the annual cycles of plant growth, animal migration, and ecological renewal that most of us associate with the changing year. This system, imperfect, sometimes dramatic in its extremes, but broadly predictable over the timescales that matter for ecosystems and agriculture, is one of the foundations of the biological abundance of Earth. Without the Moon, over geological timescales, the axial tilt would begin to wander. Consider what an axial tilt of 45 degrees would mean for the seasons. At 45 degrees of axial tilt, every point on Earth's surface would, during the course of a year, experience both an annual period of continuous daylight and an annual period of continuous darkness. Not just the poles, but latitudes well into what are now the temperate zones. The tropics would experience extreme seasonal variation rather than year-round warmth. The distribution of climate zones would be fundamentally different. Agriculture, as we know it, is built around the seasonal cycle, the timing of planting and harvest, the dormancy of fruit trees in winter, the annual migration of pollinating insects, the growth cycles of the grains and legumes that form the caloric foundation of human civilization. All of these are calibrated to the current seasonal structure. A world with dramatically different seasonal patterns would require fundamentally different agricultural systems, if agriculture were possible at all. But we are not primarily talking about impacts on human civilization. We are talking about the impacts on the entire ecology of the planet over millions of years, during most of which human civilization did not yet exist, and the ecological consequences of dramatic seasonal variation would be severe. Ecosystems are built from the interdependencies of species that have co-evolved under specific conditions. A plant flowers at a certain time because its pollinator is active at that time. A predator migrates to a certain location because its prey congregates there in a certain season. A tree drops its leaves in autumn because the temperature and photoperiod signal winter's approach, and holding leaves through winter would cost more energy than it saves. These synchronizations are precise, and they are calibrated to the current seasonal structure of the planet. Dramatically change the seasonal structure over thousands to millions of years as the axial tilt wandered, and these synchronizations break down. Not all at once, and not irrecoverably. Evolution would respond, as evolution always does, but the disruption would create extinction pressure, reduce biodiversity, and eliminate the ecological stability that allowed complex, interdependent ecosystems to develop. The temperate forests, the savannas, the wetlands, the coral reefs. All of these are the products of millions of years of evolution under relatively stable seasonal conditions. The moon is one of the reasons those conditions have been stable, and its absence over geological time would likely unravel the ecological architecture that makes Earth the biologically rich world it is today. To fully appreciate what the moon does for Earth, it helps us to look at what tidal forces do elsewhere in the solar system. Because elsewhere in the solar system, the same physics plays out in ways that are both more dramatic and more revelatory. Jupiter's moon Io is the most volcanically active body in the solar system. Its surface is a constant spectacle of volcanic eruptions, lava flows, and sulfurous geysers. The source of all this activity is not radioactive decay or residual formation heat. It is tidal heating. Io orbits Jupiter in a resonance with the other large Jovian moons. Every time Europa completes one orbit of Jupiter, Io completes two. This gravitational resonance prevents Io's orbit from circularizing, keeping it on a slightly elliptical path. As Io moves along that elliptical orbit, the tidal pull from Jupiter varies in strength, squeezing and releasing Io's interior. This constant flexing generates enormous amounts of heat through friction, melting rock and driving the volcanic activity that makes Io one of the most geologically dramatic worlds in the known solar system. Europa, Jupiter's ice-covered moon, is thought to harbor a liquid water ocean beneath its icy shell, kept liquid by tidal heating from Jupiter. The same mechanism as Io, but at a lesser intensity. The prospect that a liquid water ocean exists on Europa, preserved not by proximity to the Sun, but by the mechanical energy of tidal flexing, has made Europa one of the most compelling targets in the search for extraterrestrial life. Where there is liquid water, there is at least the possibility of life. And Europa has liquid water entirely because of tidal forces. Saturn's moon Enceladus is another extraordinary example. Enceladus is a small icy moon, but tidal heating from Saturn drives a global subsurface ocean. That ocean communicates with the surface through fractures at the South Pole, sending jets of water vapor and ice particles erupting into space in spectacular geysers that were discovered by the Cassini spacecraft. The material from those geysers has been found to contain organic compounds, the chemical building blocks of life. These examples illuminate something important about tidal forces. They are not merely a planetary curiosity. They are a mechanism for generating and sustaining the conditions for life across the solar system and beyond. The same physics that drives Earth's tides, slows Earth's rotation, and stabilizes Earth's axial tilt is also the engine that keeps Europa's ocean liquid and Enceladus's geysers active. The moon's influence on Earth through tidal forces is therefore not an isolated phenomenon. It is an expression of a universal physical law that turns out to be extraordinarily relevant to the question of where life can exist. Let us now try to draw the various threads of this documentary into a clearer picture. We have been exploring what would happen if Earth lost its moon. But the more we examine that question, the more it transforms into a different question. What did Earth gain from having the Moon? And the answer that has emerged through this journey is more encompassing than most people expect. The Moon gave Earth its tidal dynamics, the forces that shaped coastlines, drove intertidal evolution, mixed the oceans, contributed to ocean circulation, and provided the energy that early life may have used as an engine for emergence from the sea. The Moon gave Earth its stable axial tilt, the gravitational anchor that has held Earth's axial orientation within a relatively narrow range for billions of years, preventing the climate chaos that has almost certainly visited other planets and may have prevented those planets from sustaining the long-term ecological stability needed for complex life. The Moon gave Earth its current day length. By acting as a tidal brake on Earth's rotation over billions of years, slowing it from the rapid 6 to 10-hour day of the early Earth to the 24-hour day we know today. A longer day means longer periods of sunlight and darkness, different atmospheric dynamics, different thermal cycling, different conditions for biology. The Moon gave Earth its nights, not just the practical illumination that enabled the nocturnal behavior of countless organisms, but the rhythmic cycle of lunar phases that synchronized biological processes across the entire living world, from the spawning of corals to the migrations of birds. And the Moon gave Earth its history, because the giant impact that created the Moon also set in motion the conditions that made Earth what it is. The tilted axis, the partially molten interior, composition of the crust and mantle, the initial conditions from which 4.5 billion years of geological, chemical, and biological evolution would unfold. Remove the Moon from this picture, and the picture does not merely become incomplete. It becomes unrecognizable. There is a concept in the science of astrobiology, the study of the conditions under which life might exist beyond Earth, that is sometimes called the rare Earth hypothesis, proposed by paleontologist Peter Ward and astronomer Joe Kirschvink. The rare Earth hypothesis argues that the conditions required for the emergence of complex, cellular animal life are extraordinarily specific, and that meeting all of those conditions simultaneously is vanishingly rare across the universe. Most planets may support microbial life, the argument goes, but complex life, the kind of life that builds ecosystems, develops nervous systems, eventually evolves intelligence, may require a very particular combination of circumstances. A large moon is one of the conditions that Ward and Kirschvink identify. A large moon for axial stabilization, tidal dynamics, and the suite of influences we have explored in this documentary. The probability of a planet acquiring such a moon through the violent lottery of planetary formation is not trivially high. Earth's moon, as we discussed, was the product of a very specific kind of giant impact at a very specific stage of Earth development. That impact had to occur at the right angle, with the right mass ratio, at the right time, to produce a moon of the right size, in the right orbit, to have the stabilizing and tidal effects that Earth's moon has. The universe is almost certainly full of planets that formed without a large moon. Planets where the axial tilt wanders. Planets where the tidal dynamics are provided only by a distant star. Planets where the conditions for complex life are less favorable, and where the long evolutionary slog from microbial simplicity to multicellular complexity either never begins or never reaches its destination. This does not mean Earth is unique in hosting complex life. The universe is almost incomprehensibly large, containing hundreds of billions of galaxies, each containing hundreds of billions of stars, and a significant fraction of those stars hosting planetary systems. The sheer number of opportunities for life to emerge makes it likely that complex life exists elsewhere, even if the conditions for it are rare. But the rare Earth hypothesis and our exploration of the Moon's role in creating those conditions here does suggest that the combination of factors required for complex life is not casual. It is not the inevitable product of simply having a planet at the right distance from a star. It requires a particular gravitational and dynamic context, and one important component of that context for Earth is the Moon. We live on a fortunate planet. Whether we appreciate it sufficiently is another question. There is a phenomenon that occurs occasionally in Earth's sky that is, in the strict mathematical sense, one of the most extraordinary coincidences in the entire solar system. Total solar eclipses. The Sun is approximately 400 times larger in diameter than the Moon. The Sun is also approximately 400 times further from Earth than the Moon. These two ratios cancel each other out almost perfectly, meaning that from Earth's surface, the Moon and the Sun appear to be essentially the same angular size in the sky. When the Moon passes directly between Earth and the Sun, it covers the Sun's disk almost exactly, not leaving a large bright rim, not leaving the Sun mostly uncovered, but fitting with extraordinary precision over the solar disk and blocking the light from the photosphere while revealing the solar corona, the faint, ethereal outer atmosphere of the Sun that is otherwise invisible against the glare of the photosphere. This is an accident. It is not designed. It is the product of the particular size of the Moon, the particular distance of the Moon from Earth, the particular distance of the Sun from Earth, and the particular geometry of the solar system. And it is temporary. The Moon is receding, as we have discussed. Several 100 million years from now, the Moon will be far enough away that its apparent angular size will no longer match the Sun's. Total solar eclipses, the exact coincidence of a disk of exactly the right angular size, covering a disk of exactly the same angular size, will no longer occur. Future Earth will experience only annular eclipses, where the Moon's smaller apparent disk leaves a ring of sunlight visible around its edges. The window of time during which total solar eclipses are possible on Earth, with a Moon large enough to cover the Sun exactly, is defined by the Moon's recession. We happen to be living in that window. This generation, and many generations before us, and many generations after us, has the extraordinary privilege of experiencing a phenomenon that may be unique in the solar system: the accidental geometrical perfection of the total solar eclipse. Total solar eclipses have contributed historically to the advancement of science in ways that go beyond spectacle. The confirmation of Einstein's general theory of relativity, which predicted that light from distant stars would be bent by the gravity of the Sun, was first demonstrated observationally during the total solar eclipse of 1919. The bending of starlight visible during the eclipse, because the corona's faint light allowed nearby stars to be photographed during totality, matched Einstein's predictions and transformed physics. The corona itself, visible only during totality, has been the subject of intense scientific study. The mystery of why the corona is millions of degrees hotter than the solar surface, when simple intuition suggests it should be cooler as you move away from the heat source, remains one of the open questions of solar physics. Total solar eclipses have been central to the observational data that has shaped and constrained our understanding of this mystery. The Moon, in its accidental geometric relationship with the Sun and Earth, has contributed to human knowledge in ways that extend far beyond its direct physical influence on the planet. We have been asking what would happen if the Moon disappeared. But there is a related and perhaps more unsettling question. What will happen as the Moon continues to recede? The Moon is leaving at 3.8 centimeters per year. This rate itself changes slowly over time as the dynamics of the tidal interaction evolve. But projecting forward, we can sketch the broad outline of the future. In roughly 1 billion years, the Sun will have brightened significantly. Stars like our Sun gradually increase in luminosity over their lifetimes as they convert hydrogen to helium in their cores. This slow brightening will, over the next 1 billion years or so, begin to push Earth's surface temperatures above the range that most current life can tolerate. The oceans may begin to evaporate. The water vapor, rising into the upper atmosphere, will be broken down by ultraviolet radiation from the Sun, with the hydrogen escaping to space. Earth could lose its oceans over timescales of 1 to 2 billion years, becoming a drier, hotter world. This fate is independent of the Moon. It is driven by stellar evolution and is essentially unavoidable unless human civilization or some other technological intelligence intervenes. But the Moon will be present throughout this process, its stabilizing influence gradually weakening as it recedes, but still operational. Long before Earth becomes uninhabitable due to solar brightening, however, the Moon will have modestly but measurably reduced its influence. The tides will be slightly weaker. The axial stabilization will be slightly less effective. The braking on Earth's rotation will continue, lengthening the day further, in approximately 2 billion years. If the Earth and Moon system continues without major perturbation, the day will be somewhat longer than it is today. Exact figures are difficult to calculate because of the complexity of the long-term dynamics. But the trend is clear. The day continues to lengthen, the Moon continues to recede, and the tidal influence continues to diminish. At some very distant point, many billions of years in the future, if the Earth were to survive that long, the recession of the Moon would slow to a halt. Not because something stopped it, but because the day would have lengthened to the point where Earth's rotation period matched the Moon's orbital period. At that point, the same face of Earth would always face the Moon, just as the same face of the Moon already always faces Earth. This is called tidal locking, and it is the final stable state of a tidally interacting system. The Moon would appear to hang stationary in the sky, never rising or setting, visible only from the hemisphere it faces. But this endpoint is so far in the future that the Sun will have long since left the main sequence, swelling into a red giant and likely engulfing the inner planets long before Earth's rotation slows that much. The story of Earth and its Moon will therefore end not in the steady quiet of tidal locking, but in the fire of stellar evolution. It is a humbling ending to an extraordinary relationship. We have been talking about Earth and its Moon. But there is a larger question that this documentary has been quietly approaching, one that becomes more visible now that we have laid the groundwork. If a large moon is genuinely important for the emergence of complex life, and if a large moon is relatively rare among planetary systems, What does that suggest about the abundance of complex life in the universe? This question connects directly to one of the most famous unsolved problems in all of science, the Fermi paradox. In the 1950s, physicist Enrico Fermi was having lunch with colleagues and discussing the possibility of extraterrestrial civilizations. Someone mentioned the apparent plausibility of there being many intelligent civilizations in the galaxy. And Fermi asked, simply, where are they? If intelligent life is common in the galaxy, and if civilizations develop technology capable of interstellar communication or travel, we should expect to see evidence of them. Signals, artifacts, some indication that the galaxy is occupied by minds other than our own. Yet the sky is silent. The search for extraterrestrial intelligence has, so far, found nothing. This silence, the apparent emptiness of a universe that ought, by naive calculation, to be teeming with civilizations, is the Fermi paradox. There are many proposed explanations. Perhaps intelligent life is genuinely rare. Perhaps civilizations tend to destroy themselves before reaching the capability for interstellar communication. Perhaps they are out there, but are not communicating in ways we can detect. Perhaps the distances involved are simply too vast for any signal or artifact to have reached us yet. The rare Earth hypothesis and the Moon's role within it suggests one possible contribution to the answer. Perhaps the conditions required for the emergence of complex, intelligent life are genuinely rare. A planet at the right distance from the right kind of star is necessary but not sufficient. It also needs, perhaps, geological activity to recycle nutrients and regulate the carbon cycle. It needs a sufficient supply of heavy elements from earlier generations of stars. It may need a gas giant like Jupiter in the outer solar system to intercept the most devastating potential impactors. And it may need a large moon to stabilize its axial tilt and drive the tidal dynamics that favor the evolution of complex life. Each of these requirements independently reduces the fraction of planets that qualify. Together, they may reduce that fraction to something very small indeed, even in a universe containing hundreds of billions of galaxies. This is not a proven argument. Astrobiology is a young science, and our sample size of inhabited planets is currently exactly 1. The Moon's role in making Earth habitable is significant, but how necessary it was. Whether there are alternative pathways to complexity that do not require a large moon is genuinely unknown. But the question itself, emerging naturally from the investigation of one particular moon orbiting one particular planet in one particular solar system, opens onto the deepest questions in science. Questions about the prevalence of life, about the rarity of intelligence, about our place in the cosmos. Questions that the moon, hanging in the sky above, has been silently holding for 4.5 billion years. There is a chapter of this story that is often overlooked, and it is a chapter about what the moon has preserved. The moon has no atmosphere. It has no liquid water. It has no active geology, no plate tectonics, no volcanism in the modern era, no erosion from wind or rain. Its surface has not changed significantly for billions of years, except through the slow accumulation of impact craters and the deposition of the solar wind and interplanetary dust. This makes the moon one of the most remarkable archives in the solar system. The Earth, by contrast, is a dynamic and restless world. Plate tectonics continuously recycles the oceanic crust. Erosion wears down mountains, sediment buries, and transforms ancient rock. The geological record on Earth extends back roughly 4 billion years in isolated fragments. But the first 500 million years of Earth's history, the Hadean Eon, are almost entirely absent from the terrestrial geological record. Conditions were too violent, too active, too transformative for rocks from that era to survive. The Moon's surface, however, preserves a record of the early solar system that Earth cannot. The rocks returned by the Apollo missions have given us direct access to the geological history of the Moon across its full 4.5 billion year lifetime. They have told us about the late heavy bombardment, a period approximately 3.9 to 4.1 billion years ago, when the inner solar system was subjected to an intense rain of asteroid and comet impacts. The evidence for this bombardment is written in the densely cratered ancient highlands of the Moon, which predate the Maria. The dark basaltic plains that fill the Moon's large impact basins. The late heavy bombardment was a defining event in the early history of both Earth and the Moon. On Earth, the traces of this bombardment have been almost entirely erased by geological activity. On the Moon, they are preserved in the landscape. Understanding the late heavy bombardment matters because it constrains the timing of life's emergence on Earth. If the bombardment was as intense as the lunar evidence suggests, early life would have faced an extraordinarily hostile environment, with large impacts capable of vaporizing entire oceans. Yet despite this, evidence suggests that microbial life was already present on Earth by at least 3.5 billion years ago, and possibly earlier. Life emerged and managed to survive the bombardment, or emerged in the aftermath. The Moon is therefore not merely a companion to the Earth. It is a witness to Earth's earliest history. A witness whose testimony is preserved in rock and crater in a way that Earth itself cannot provide. The Apollo samples, 382 kilograms of moon rock, returned between 1969 and 1972, remain among the most scientifically valuable materials in human possession. They have been studied continuously for more than 50 years, and they continue to yield new insights as analytical techniques improve. Researchers today can extract information from Apollo samples using instruments that did not exist when the samples were collected, and the lunar surface contains much more that has never been sampled. Future missions to the Moon, including the Artemis program, the Chinese Lunar Exploration Program, and planned international collaborations, will return additional samples and conduct additional measurements that will deepen our understanding of early solar system history in ways that are currently impossible to anticipate. The Moon is not merely a body to be visited. It is a geological library, and its pages have been accumulating records for 4.5 billion years, waiting to be read. There is a dimension of the Moon's influence that we have not yet properly addressed, and it is perhaps the most difficult to quantify, but the most immediately human. The Moon shaped human culture, not in the metaphorical sense of inspiring art and poetry, though it did that too, in the more fundamental sense that the visible, regular, predictable cycle of the Moon may have contributed to the development of abstract thought itself. The ability to recognize patterns, to observe that the Moon grows bright and then dark over a regular cycle, to count the repetitions, to predict when the next full moon will occur, requires a specific kind of cognitive capacity. It requires the ability to track time abstractly, to count, to form expectations about future events based on past patterns. These are foundational cognitive skills, and they may have been among the earliest abstract cognitive operations that ancestral humans developed. The oldest confirmed calendrical tools found in the archaeological record are engraved bones with sequences of notches that many researchers interpret as records of lunar cycles. Some of these artifacts are more than 30,000 years old. They suggest that Paleolithic humans were tracking the moon's cycle systematically, not just noticing it, but recording it, which means they were using the moon as the basis for a form of timekeeping that extended beyond the span of individual memory. The connection between lunar tracking and the development of abstract thought is speculative. The causal relationships between environmental conditions and cognitive evolution are extraordinarily complex and not easily reconstructed from archaeological evidence. But the correlation is striking. The moon provided one of the most visible and regular patterns in the natural world, a pattern that changes on a timescale human beings can observe directly within their own lifetimes. And that could be tracked with simple marking tools. It was a ready-made teacher of pattern recognition and temporal abstraction, mathematics, navigation, agriculture, astronomy. All of these developments in human civilization were connected, in their early stages, to the tracking of celestial cycles. The moon's cycle was the most accessible and regular of those cycles, and the cognitive habits that lunar tracking may have helped develop, counting, predicting, abstracting, are the cognitive habits that underlie civilization itself. Whether the moon deserves credit for human intelligence is a claim too strong to make. Human intelligence is the product of millions of years of evolution driven by a vastly complex set of pressures. But the possibility that the moon provided early humans with one of the most powerful cognitive training grounds available in the natural world, a regular, visible, predictable pattern that rewarded attention and tracking, is a thought worth sitting with. We are, at this moment in history, in the early stages of a renewed era of lunar exploration. The Artemis program, led by NASA in collaboration with international partners, aims to return human beings to the moon for the first time since Apollo 17 in 1972. China's lunar exploration program, the Chang'e series, has successfully landed rovers on the moon, including on the far side, which has never been directly visited by any previous mission. The Indian Space Research Organization's Chandrayaan-3 mission successfully landed near the moon's south pole in 2023. Multiple private companies are developing lunar landers and surface systems. The moon is, once again, a destination. Why? The reasons are multiple and interlocking. Scientific reasons. The moon's south pole regions are thought to harbor water ice in permanently shadowed craters, preserved for billions of years without evaporation, in the absence of an atmosphere and in the permanent cold of deep shadow. This water ice could be a resource for future lunar activities, as drinking water, as a source of oxygen for breathing, or as propellant for spacecraft. The presence of water ice also means the presence of other volatile compounds that may have been delivered to the moon by comets and asteroids over billions of years, providing a chemical record of the early solar system's composition. Strategic reasons. The moon represents the next step in human expansion beyond Earth. A sustained human presence on the moon would develop the technologies, the operational experience, and the supply chains needed for eventual crewed missions to Mars and beyond. Economic reasons. The moon may harbor resources, not just water ice, but helium-3, a rare isotope on Earth that is abundant in the lunar regolith as a result of billions of years of solar wind implantation. Helium-3 is of theoretical interest as fuel for nuclear fusion reactors, though fusion power itself remains a technology of the future, and perhaps most fundamentally, inspirational reasons. The Apollo missions transformed human self-understanding. They provided one of the most powerful collective experiences of what human beings are capable of when they direct their ingenuity and resources toward a common goal. They produced the famous photographs of Earth rising above the lunar surface, images that contributed to the environmental movement by providing a visual representation of Earth as a single, finite, fragile body suspended in the blackness of space. A renewed era of lunar exploration promises to produce analogous transformations in science, in technology, and in human self-understanding. Let us return one final time to the thought experiment that opened this documentary. The moon has disappeared. You are standing outside. The sky is clear and dark in a way it has not been in your lifetime, and the stars are visible in numbers that startle you. The Milky Way spreads across the sky in a band of cold light, the billions of stars of the galactic disk stretching from horizon to horizon. It is, in a purely astronomical sense, more beautiful than a night with the moon. But something is wrong. The tide tables that have organized coastal life for centuries are no longer accurate. The fishermen who set their schedules by tidal patterns are discovering that the patterns have changed. The coral reefs are confused. The spawning events that are supposed to happen at the full moon are not happening because there is no full moon. The shorebirds that time their migration to arrive at the horseshoe crab spawning are arriving to find that the spawning is disrupted. In the years that follow, the ecological disruptions multiply. Some species adapt, others do not. The intertidal zone narrows as the solar tides produce a smaller tidal range. The tidal mixing in the ocean decreases, and fisheries in certain regions begin to show declining productivity. The night sky without the moon becomes brighter with stars but darker in a way that feels wrong, as if a permanent overcast has descended on some unconscious layer of human experience. Culturally, the loss is incalculable. Every religion that incorporates a lunar calendar, and there are many, must restructure its observances. The concept of the month, derived from the moon's cycle, and baked into language and timekeeping across virtually every human culture, becomes a relic, a unit of time named after an object that is no longer there. And over the following millions of years, the changes accumulate. Without the moon's stabilizing influence, Earth's axial tilt begins its slow wandering. Centuries pass and the change is imperceptible. Millennia pass and the change is measurable, but not catastrophic. Millions of years pass and the climate zones have shifted. The tropics, once warm and stable, now experience dramatic seasonal variation as the tilt climbs toward angles that currently exist nowhere in the solar system's inhabited history. The ecosystems that complex life took hundreds of millions of years to build begin to unravel at the edges. Not all at once. Evolution responds as it always does. Some species find ways to persist, but the extinctions accelerate. The biological richness of the planet, the extraordinary diversity of life that has accumulated over the long, relatively stable history of Earth, gradually diminishes. In 50 million years, Earth looks different. In 100 million years, it looks dramatically different. The planet is still alive. life is extraordinarily resilient, and microbial life in particular is nearly indestructible under conditions far harsher than any axial wandering would produce. But the era of complex animal life, of ecosystems built from intricate interdependencies, of the rich biological tapestry that currently covers this world, that era may be abbreviated. Whether it would be abbreviated by millions of years or by hundreds of millions of years, no one can say with certainty. The details depend on orbital mechanics that are difficult to model across such timescales, and on biological responses that are inherently unpredictable. But the direction is clear. The moon is holding something in place, something that took billions of years to build. There is a paradox at the heart of this documentary. We began by imagining the moon's absence as a way of understanding its presence, and in doing so, in tracing the consequences of losing the moon across timescales ranging from a single night to billions of years, we have arrived at something that cannot be seen directly from the moon's presence alone. The moon is invisible in its most important functions. You can see the tides, but most people do not think about the role of tidal mixing in ocean productivity. You can see the moonlight on a clear night, but most people do not think about the biological synchronization that moonlight enables. You can see the moon hanging in the sky, but you cannot see it stabilizing the axial tilt, or slowing the rotation, or transferring angular momentum outward in a billion-year gravitational dialogue with the Earth. The moon's most consequential functions are, paradoxically, the least visible ones. This is true of many of the most important systems on which life depends. The invisible atmosphere that filters radiation and moderates temperature. The invisible magnetic field that deflects the solar wind. The invisible chemical cycles. The carbon cycle, the nitrogen cycle, the water cycle, that maintain the conditions for life within their current ranges. The invisible gravitational architecture of the solar system that keeps the planets on stable orbits and shields the inner planets from the most devastating potential impactors. The conditions for life are largely invisible. They are the background against which everything else occurs. And because they are the background, they are easily overlooked, easily taken for granted. The moon is part of that background. It has been part of it for 4.5 billion years. It was there before the first cell divided. It was there when the first complex organism assembled from cooperating cells. It was there when the first fish crawled onto a mudflat at the edge of a Devonian sea, trying the unfamiliar texture of air for the first time. It was there when the first forests grew, when the first flowers bloomed, when the first human hand turned a piece of bone over and began to mark its surfaces with a sequence of notches that counted the days. It has always been there, so consistently, so reliably, that it became the most familiar thing in the sky, and consequently, perhaps, the thing most easily overlooked in any accounting of why life on this planet is possible. On the night of July 20, 1969, two human beings stood on the surface of the moon. Neil Armstrong and Buzz Aldrin spent approximately 2.5 hours on the surface in their first moonwalk. They planted a flag, collected samples, set up experiments, and spoke to the President of the United States via radio. And they looked up at Earth, a blue and white sphere, vivid against the absolute black of space, and experienced something for which no previous human experience had prepared them. Armstrong later described the experience of holding up his thumb and realizing that it was large enough to cover the entire disk of Earth, to hide behind a single extended thumb. everything that any human being had ever known, every place any person had ever lived, every person who had ever existed. That gesture, that realization, has been described by multiple Apollo astronauts as a transformative moment. Not frightening, but clarifying. A perspective that reshapes everything that follows it. The moon made that perspective possible, not merely by providing a surface to stand on, but by being the place from which Earth becomes visible in its entirety. Finite, fragile, luminous, suspended. Everything we have explored in this documentary. The tides, the axial stability, the slowing day, the intertidal evolution, the biological rhythms, the climate regulation, the geological archives. All of it amounts to the moon, holding in place the conditions for the existence of the beings who would one day travel to its surface and look back. There is something extraordinary in that. The moon shaped the conditions for the emergence of curiosity, and then curiosity directed itself back toward the moon. The object that enabled the existence of the observers became the destination of those observers. The thing that held the world in place was visited by the world it had held. We have been exploring what would happen if Earth lost its moon. But what we have actually uncovered is what it means that Earth has its moon. What it means that the collision 4.5 billion years ago produced exactly the companion that would, over billions of years, hold the axial tilt, steady and drive the tides, and slow the spinning day, and anchor the conditions for the emergence of the life that would eventually stand on its surface and look home. None of this was designed. None of it was intended. It was the product of physics and gravity and chance. The same physics and gravity and chance that govern everything else in the universe. And yet the outcome, surveyed from the vantage point of a species that has spent centuries learning to understand it, is astonishing. We are near the end of this journey. But there are questions that this documentary has deliberately left open, because they are genuinely open. Not open due to any failure of inquiry, but open because the science itself is still actively unfolding. Does the moon's influence on Earth's axial tilt guarantee complex life would not have evolved without it? No. It makes it less likely, and potentially much less likely. But certainty is not available. Would life on a moonless Earth have found different but equally effective pathways to complexity? Possibly. Evolution is creative in ways that are genuinely difficult to predict. And the history of life on Earth is full of examples of multiple independent evolutionary solutions to the same challenge. Maybe complex life on a moonless Earth would have found ways to thrive under conditions of greater axial variability. We do not know. Are there planets in the universe with large moons, stable axial tilts, and the other conditions for complex life? Where complex life has indeed emerged and perhaps developed intelligence? Almost certainly, given the scale of the universe. The Drake equation, the framework for estimating the number of communicating civilizations in the galaxy, remains deeply uncertain in most of its terms. But the sheer number of planetary systems that exist makes the emergence of at least some with Earth-like conditions, including a large moon, statistically plausible. Is the moon's influence on life the single most important factor in Earth's habitability? No, there are many factors that matter. The sun's stability, Earth's position in the habitable zone, the presence of plate tectonics, the carbon cycle, and its regulation of atmospheric composition, the presence of liquid water, the timing of oxygenation of the atmosphere. The moon is one important factor among several. Its importance should be neither understated nor overstated. What is the future of the moon's influence on Earth? Gradual diminishment over geological timescales as the moon recedes and the tidal forces weaken. On any human timescale, the changes are negligible. On geological timescales, they are real and accumulating. Will we ever know for certain what Earth would have been like without the moon? No. Counterfactual history, the history of what did not happen, is not accessible to empirical science. We can model it, simulate it, reason about it. We cannot observe it. The best we can do is understand the mechanisms of the moon's influence well enough to draw well-reasoned inferences about its absence. And those inferences, as this documentary has attempted to show, paint a compelling and sobering picture. A clear night. The stars are bright. The familiar silver disk of the moon hangs in the sky, right where it has always been, right where it was on the first night of human history, right where it will be. Broadly speaking, in the same part of the sky, following the same path, for millions of years to come. You have just spent hours learning about what it does. You know now that the water moving across the beach below is moved partly by the gravity of that disk of light, that the angle at which the seasons come is held steady partly by its mass, that the day you are living through is the length it is because, over billions of years, the moon stole some of Earth's rotational energy and carried it outward, that somewhere in the ocean right now, nutrients are being carried upward by tidal currents that would be weaker without the moon's pull, that somewhere on a coral reef, the rhythms of reproduction are calibrated to the lunar cycle that you can see tracking across the sky. The moon looks the same as it always did, round and silver and ancient and silent. But it is not quite the same as it was before you began this journey. The object has not changed. Your understanding of it has. And that is, perhaps, what the best science documentaries are ultimately for. Not to replace the familiar with the technical, but to add layers of meaning to the familiar, so that what was ordinary becomes extraordinary, and what was background becomes foreground. The moon is not decoration. It is infrastructure. It is the gravitational partner of this planet, engaged in a slow, continuous 4.5 billion year collaboration that has shaped everything from the length of the day to the evolution of the first land animal to the calendar systems of every human civilization. It is, in every meaningful sense, part of why you exist. And it is still there, tonight, and for billions of years to come, receding slowly, weakening gradually, but present and real and doing what it has always done, hold the world in place. There is one final thought. The universe is approximately 13.8 billion years old. For the vast majority of that time, there was no one to observe it. No eyes, no minds, no instruments capable of measuring the distance to the nearest star, or the age of the oldest rock, or the mass of a distant moon. The universe was happening, but it was not being observed. Somewhere in the last few 100,000 years, a vanishingly small sliver of cosmic time. A species on a small planet around an unremarkable star in the outer regions of an ordinary galaxy began to develop the cognitive capacity to ask questions about the universe itself, to wonder, to measure, to build instruments that could see further than any biological eye, to reason from the evidence of rocks and fossils and starlight toward an understanding of what happened 4.5 billion years ago and what is happening right now in the cores of stars 1,000 light years away. We are, as far as we currently know. The only part of the universe that is aware of the universe. The only part of the 13.8 billion year story that is actively trying to understand the story and the conditions that made that awareness possible. The conditions that allowed this particular species to evolve on this particular planet include, in ways that this documentary has tried to trace, the presence of a large moon, a gravitational companion that has been stabilizing and regulating and influencing this world since before the first cell divided. The moon enabled the conditions for the emergence of the beings who now study the moon. There is a strange beauty in that, not a designed beauty. Nothing about the universe requires a designer for it to be beautiful. The beauty is in the structure of it, in the way that the same physical laws that govern the collision of two protoplanets 4.5 billion years ago also govern the movement of water across a beach on a summer evening, and also govern the orbit of the spacecraft that carries human beings back to the surface of the moon, and also govern the gravitational lensing that allows us to study galaxies billions of light years away. Physics is the same everywhere, and the same physics that made the moon also made the beings who wonder about the moon. The universe, perhaps, is not as indifferent to itself as it first appears. At least here, on this particular planet, something remarkable happened. Matter organized itself into patterns complex enough to turn around and look at itself, to ask where it came from, to notice the moon in the sky and begin, slowly and patiently and with enormous effort, to understand what it does. That understanding, incomplete, always incomplete, forever approaching but never fully reaching, is what we have been doing in this documentary, and what we will continue to do, because the questions do not end. They deepen. What would happen if Earth lost its moon forever? We would lose the tides, and the axial anchor, and the biological rhythms, and the lengthening day, and the intertidal zones that drove life from the sea. We would lose the nights full of silver light that have been falling on this world for 4.5 billion years. And we would lose, perhaps, the most enduring reminder that the universe we inhabit is not merely large and old and mostly empty. It is, in at least one known instance, arranged in a way that allows complexity to arise and curiosity to develop, and a species to look up at the nearest large piece of rock in the sky and spend hours and years and lifetimes trying to understand what it means. The moon is still there. Look up.